Hello students. In the last class, we were talking about the backtracking. So in backtracking, you know that we need to construct a state space tree. In a state space tree, I'll start once again. I'll repeat once again. In the last class, we were seeing about the backtracking. The backtracking is to construct a state space tree, which will be consisting of two components, the nodes and the edges. The nodes will be leading to the partial solution and the edges are giving you the choices in extending your partial solutions. Now, what is the technique which we follow for generating the state space tree? It is nothing but the depth first search. So by using the depth first search technique, we are going to generate the state space tree and we will be getting the solution. So when you generate the state space tree, you will be considering, given any problem, there will be some constraints. So when you say that there are certain constraints to be satisfied, you will be seeing what are the constraints for a given problem. So based on the constraints, you will be seeing whether you will be going for a particular problem to be solved by using the backtracking method, in which you have two types of nodes. One is your promising nodes and another one is your non-promising nodes. Promising nodes will always lead to a partial solution. The partial solution will further generate to a complete solution. When you say it as a non-promising nodes, it is also called as a pure nodes, where when you expand this, you will be seeing that by using the depth first search, you will be exploring the subtrees, and you will be, when the nodes doesn't lead to a solution, we say that we backtrack it, go to the parent node and continue the search with another edge or another path or another option. So here you are given with this Hamiltonian circuit. What do you mean by Hamiltonian circuit? Hamiltonian circuit problem is nothing but it is as similar to a traveling salesperson problem. We have already seen the traveling salesperson problem in the second module, where we are using the brute force method to obtain the solution for a traveling salesperson problem by using the SOS search. The SOS search says that you need to generate all the paths, okay, and among the paths you will be considering an optimal solution which gives you a minimum value. So for a traveling salesperson problem, we consider the graph, the input is a graph, and we consider the traversal of the graph by taking all its edge weights, okay, or the cost for each and every edge. But whereas in Hamiltonian circuit, we just ignore the cost. So we have seen in the introduction, there are different types of graphs. The graphs can be a directed graph, undirected graph, weighted graph, non-weighted graph, etc. So here you are given with a problem which is an undirected graph plus a non-weighted graph also. Why? Because while you consider the Hamiltonian circuit, we just discard the edge cost. We just take the path or a circuit is created by starting with a particular vertex. We will be covering all the vertices exactly once and come back to the starting vertex. That is nothing but it is called as the Hamiltonian circuit. If the Hamiltonian circuit exists, we assume that it is going to start with a vertex A. And when there are different choices, we go traverse it according to the alphabetical order, because always when you say it as a graph, based on the notations used, if it is alphabets, we go according to, if there is a tie up, if there are three paths, It's nothing but a tie-up. How to break this tie-up? The tie-up is broken by going it or traversing it through the alphabetical order. If the graph vertices are numbered as numeric values, then we will be following the ascending order or the sorted order. So here, when you have a graph, it will be starting with the root of the state space tree. Then from that root, it will be traversing through all the vertices, forming a cycle. Ensure that you visit all the vertices exactly once and coming back to the starting vertex. For example, if you say it as you are traversing through A to B, B to F, F to E, E to C, C to D, and back to A. So all these vertices, suppose if here, how many vertices are there? The number of vertices given are 6. So you will be starting with vertex A. All the remaining 5 vertices will be visited exactly once and come back to the starting vertex. So that is nothing but it is called as the Hamiltonian circuit. See, in this graph, there are many circuits. If you are asked in the question paper, if you are asked for creating a single path, you stop the generation of the tree structure by giving one solution. But suppose if you are asked for finding out the different paths, you will be generating the entire tree structure, obtain all its solutions. The various solutions obtained for a single problem are the different circuits. But certain cases, then you will not be able to get a circuit at all. Okay, there will not be any existence of a circuit. So we need to find out whether you can get a circuit, and if at all it is a circuit, which means that you start with a vertex, ending with the same vertex by visiting all the vertices exactly once. This is nothing but the Hamiltonian circuit problem. Now, the next is how to do it. How to generate the state space tree by using the backtracking method. As we have seen already, backtracking method, we are following the DFS. So it is a depth first search. So we start with a particular vertex, and here we are assuming that we are going to start, if at all there is any existence of a circuit, we start with the vertex A. So now, what are the 3 options? The 3 children are either you can go to B, or we will be able to go to C, or we will be going to D. So now, here there are 3 choices. Since there are 3 different paths, 3 choices available, it is nothing but it is a tie. The tie has to be broken. How the tie will be broken arbitrarily? By going according to the alphabetical order. So going according to the alphabetical order is nothing but it says that since there are 3 choices based on alphabetical order, we just start with B. Now, when you start with B, again for B, this node is already visited. So you cannot consider this choice. You have only 2 choices left out. The 2 choices are it can either traverse to C or it can traverse to F. Now, if it traverses to C, first we will see how to get the path by traversing it to C. If you traverse it to C, for C, what are again the 2 options? There are 4 options, A, B, D and E, but don't consider A and B. A and B are already visited. Okay, while doing the 2 traversals, breadth first search and depth first search, we are seeing that each node, when it is visited, we will be marking it as visited, and we will be only traversing through the next vertex to be traversed will be always an unvisited one. So for C also, there are 2 unvisited vertices, D and E. So first start with D. So here we have D. Now, this is the 3rd node which has been visited. Now from D, you have the path to E. We have A also, but you cannot consider A. Why? Because A is the starting vertex. It can be visited again only if you complete all the remaining vertices. If all the remaining vertices are visited exactly once, then you can come back to A. Until Unless you visit all the remaining vertices, you are not supposed to come to A. If you are coming back to A, then it is not a Hamiltonian circuit. So as I told you, each and every problem has certain constraints. The constraint here is starting with A, visiting exactly once all the other remaining vertices and coming back to A. So from D, we are moving further to E. Now from E, we are again moving further to F. From F, is there any path exist for moving to A? No. Since there is no edge from F to A, we cannot consider this as the solution. So this becomes a non-promising node or a dead end. So whenever you encounter a dead end, what we need to do? We need to backtrack. Going back to E. When you go back to E, do you have any other options? No. You go back to its parent. Here for D, is there any option left out? No. Go back to its parent, C. For C, there were two choices, D and E. We have only done with D, so now we are moving to E. Now, when you go to E, what is the next option? From E, there are two options, D and F. According to the alphabetical order, we take the child as D. First option is D. Now, from D, you can, even though there exists an edge from D to A, we are not supposed to go to A because we need to cover the vertices which are left out. What is left out? Vertex F is not been visited. Since F is not visited, even though there exists, in our previous case from F to A, there doesn't exist an edge. But in this case, from D to A, there is existing an edge, but we cannot go. Why? Because we have left out one of the vertex among the remaining vertices. What is the vertex which is unvisited? F is not visited at all. So it becomes a dead end. There is no path existing, no edge existing from D to F. If there exists a path from D to F and F to A, you could have got a solution. But since it is not there, it becomes a dead end. So from E, we have one more option. That is, from E, we can either move to D or F. D becomes a dead end. So we are going for the next child. The next child is F. F again becomes dead end. Why? From F to D, there is no edge. So we cannot consider. So we are going back to E. E, there were only two options. Both options were worked out. So we are backtracking, moving to its parent. Again, for C also, we had only two options, D and E. Both are worked out. So we are moving back to B. Now, when you move back to B, actually there were two options, C and F. We have worked out with the C. So what is left out? The left out is F. So we are going to F. Now from F, there exists an edge from F to E. So we are going to E. Now from E, you have C and D. There is a tie. How the tie has to be broken? The tie can be broken arbitrarily by choosing the alphabetical order. So from E, we are next moving to C. Now from C, we move back to D. Have you traversed all the vertices, remaining vertices? Yes. All the remaining vertices like B, C, D, E, F, all are visited exactly once. So now, is there any path exist between D to A? Yes, it exists. Since there exists a path from D to A, after visiting all the 5 vertices, we have come back to A. Starting with A, ending with A by visiting all the vertices exactly once. So here we get a solution. Have you understood? Is it clear? Starting with A, traversing all the vertices exactly once, coming back to A, which gives you a Hamiltonian circuit problem solution. So first, when you have a tie, the tie has to be broken arbitrarily. Second, even if there exists a path to go back to A, you should also recheck, confirm it whether you have visited all the remaining vertices exactly once. In this case, there doesn't exist an edge from F to A, so it became a dead end. In these two cases, among 5, 1, 2, 3, 4 only were visited. one was left out. Until unless you visit the all the 5, you cannot go back to A. So even though there exists a path from D to A, we couldn't go to it. Why? Because one of the vertices was left out. Okay, so if you are asked for a constructing a single solution, constructing a single circuit, constructing a simple Hamiltonian path, you can stop the generation of the tree structure here. But if not, if you are asked for obtaining all the solutions, you need to try out for all. For example, in the first case, we have tried out with A, we moved to B, then from B, you have moved to the other vertices. Now only one branch is over. What is the next option? Now we can go to C. So when you go to C, you can see that from C, again we will be traversing to B. C, you have two options, D and B. Which one we will be preferring? We will prefer B. From B, you are moving to F. From F, you are moving to E. From E, you are moving to D. From D, you are moving to A, which is your starting vertex. And here we have completed all the vertices exactly once and you are getting a solution. Similarly, from A to C, you have two options, B and D. B is done with. So now we will move to D. Now when you go to D, from D you are going to E. From E we are moving to F. F we are moving to B. And from B there exists an edge to A where you are getting another solution. Clear? So there were three options. So we have seen how to go ahead with B. The next choice is how to go ahead with the C. One more is left out, how to trace with the help of D. Now, when you take D, there are two options, C and E. So first we will work out with C. Now from C, we are moving to B. From B, you are moving to F. F, you are moving to E. It becomes a dead end. Why? Because we cannot go back to A. Even though all the vertices are visited exactly once, we cannot go. There is no path from E to A. So that becomes a dead end. Similarly, C is having two options. Either you can go to B or you can go to E. So even if you take E also, E, if you take, you will be getting it as E to F, F to B, B to A. We will be getting a solution. Next, we will be going with C. We have found out a solution. Now we will go with D. There are two options, C and D. So we will work out with E. Now when you go with E, what is the next option? It is C. So from C, we are moving towards to B. From B, you are moving towards to F. From F, there is no edge towards back to A. So it becomes a dead end. Backtrack, go to B, no more option. Go to C, no more option. Go to E, there is one more option. For E, you have from A, we are going to D. From D, we are going to E. From E, we have two options, C and F. C is already completed, so we will move on to F. Now, when you take F, from F, you can move to B. From B, you can move to C. From C, you can move to A, which is your solution. Clear? So, here for a Hamiltonian circuit, if you are given with a graph, assume that we are starting with A. Since we are starting with A, we are ending with A by traversing through all the vertices exactly once, and it forms a cycle also. So if you are asked to find out a solution, you just traverse the tree structure, get a solution. If you are asked for finding all the Hamiltonian circuits or Hamiltonian paths, generate the entire tree structure to get all the solutions. So if at all there is a tie, the tie has to be broken. How the tie will be broken? The tie will be broken based on what is that you are following for your vertices. If it is alphabets, go according to alphabetical order. If it is numbers, numeric values, you go according to the sorted order or the ascending order. So if whenever you go, if you find that there doesn't exist a path back to A, it becomes a dead end. Or if you find that one of the vertices are not been visited, there also you will be saying that it is a dead end. So these two are the cases. Here we have, even though we have covered all the vertices, there is no edge from F to A. So we are saying that it is a dead end. Here, one of the vertices is left out. Which vertex is left out? We have covered B, C, E and D. F is not visited. So here we are saying it as a dead end because even though D to A there exists an edge, F is not visited. Since it's not visited, we say that it is a dead end. If you are able to visit all the vertices exactly once and come back to the starting vertex, then we get a solution. So try out this problem to find out, not with a single solution, with multiple solutions. For a Hamiltonian circuit, you have multiple solutions. What are the solutions? The solution starts with A, ends with A by visiting all the vertices exactly once. So here, some of the solutions are been already solved for you. So try out, can you, whether you, it is possible for getting any solution or any dead ends which are left out. Here for C, we have two options. Only one option is worked out. So you try for the other one and get the solution also. Okay. So there will be 5 different solutions for this Hamiltonian circuit. I want you to work out this problem, get the solutions. The complete tree structure has to be generated. This is only a partial tree structure. You can see only one of the vertex has been, one of the child has been tracked. You will be similarly, we can go for C, D, everything which I have done for you partially, but you need to complete the entire tree structure to get all the 5 solutions. Clear? So that's all about your Hamiltonian circuit. So Hamiltonian circuit also comes under the backtracking, where you are going to generate the tree structure. So this tree is nothing but it is called as the state space tree. So there are 2 things. One is nodes, which are the choices, and another one is the edges. The edges are the choices which may lead to a partial solution. If it is a partial solution, we are going further. If it is a non-promising or pure node, it is considered to be a dead end. We need to backtrack. Move to its parent, see other choices. If there are no more choices, again move to its previous level, go to its parent node. So this will be repeated again and again till you get a solution. So that's all for today, where you will be, you have seen the 2 examples of backtracking. Both are equally important. One is your NQN problem and another one is your Hamiltonian circuit. Now there exists one more problem. So tomorrow we will be seeing the sum of subset problem and see how it can be solved by using the backtracking algorithm. Okay, so we'll be stopping it over here.